Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 7 of this lecture series on jet aircraft propulsion. In the last lecture, I had given you some introduction to what is meant by the Joule-Brayton cycle, which is basically the thermodynamic cycle based on which all the jet aircraft engines operate. Basically the jet aircraft engines operate on the Brayton cycle. So, we were discussing about the ideal Brayton cycle, and also towards the end of the previous lecture, we also had some discussion on what could be the deviations from the ideal cycle because of irreversibilities occurring in the various processes. For example, the compression process for an actual cycle is non-isentropic. So is the expansion process, which happens to be non-isentropic. There are also pressure losses which occur in the heat addition and heat rejection processes. So, all these irreversibilities put together make the Brayton cycle non-ideal for actual engines. And so, what we will be discussing today is application of the Brayton cycle for jet aircraft propulsion, and how is it that the different forms of jet aircraft propulsion use the basic Brayton cycle for their operation. So, let us take a look at what we are going to discuss in today's lecture. We will be talking about, we will begin with the basic thermodynamic cycle which is used for jet aircraft engines, something we have discussed in the last lecture. Then one of the most common or the basic fundamental forms of the jet engine is the turbojet engine. You have already had some introduction to turbojet engines in some of the earlier lectures. Today we will discuss about the cycle based on which the turbojet engines operate. We will then discuss about turbojet engine with afterburning, and then we will talk about turbofan engines and its variants. There are different types of turbofan engines, then turboprop and turboshaft engines, and also a very quick look at ramjet engines. We are going to discuss about ramjet engines towards the later half of this lecture series, but we will just spend a few minutes on discussing about ramjet engines as well. Now, as we have seen in the last lecture, Brayton cycle involves at least the ideal Brayton cycle involves 4 processes. The first process is in the ideal cycle, it is the compression process, an isentropic compression, which raises the temperature and pressure of the working fluid. At the end of the compression process, the heat addition process takes place, which occurs at a constant pressure for an ideal cycle. And then after the heat addition process, we have an expansion process, and for an ideal cycle, that is an isentropic expansion, and then there is a heat rejection process. And so, all these 4 processes put together complete the Brayton cycle. Now, Brayton cycle by its very nature is a closed cycle, which means that it is the same working fluid that is used continuously in the operation of the cycle. But aircraft engines which operate based on the Brayton cycle operate in the open cycle mode, that is, they do not use the same fluid all over again, but just that for example, if an aircraft is cruising at a certain altitude, the temperature and pressure can be assumed to be more or less constant, and so we can assume that whatever fluid is coming in is it's the same fluid that keeps coming in all over again. And so, using air standard assumptions, we can kind of approximate the jet engines to which basically are open cycle engines towards a closed cycle Brayton cycle form. So, gas turbine engines, all jet engines operate on the Brayton cycle in some fundamental sense, but of course, the actual form of these engines are much different in the sense that none of the processes are isentropic or constant pressure and so on. So, all the processes involve some form of irreversibility or the other, and therefore, the actual engines are quite different from, or the cycles are slightly different from the ideal Brayton cycle. And so, in an ideal Brayton cycle that we have discussed in the last lecture, wherein the cycle was assumed to have been operating in a closed cycle mode, For a jet engine, it can still be assumed, but with certain approximation with air standard assumptions and so on, we can still assume that the jet engine the jet engine also operates on the Brayton cycle mode. Now, in an ideal cycle, we have seen that it does not assume any irreversibilities and that air behaves as an ideal gas with constant specific heats and no frictional losses, etc. This will still be true for ideal jet engine cycles, but when we discuss about the actual or real jet engine cycle, which we will discuss in later lecture, we will see that we will have to account for all these variations. How we will do that is something we will discuss during that particular lecture. Now, so the most basic form of jet engine is the turbojet engine. A turbojet engine is the fundamental form of a jet engine, and there are many variants of turbojet engine as we see it today, depending upon the different applications. For example, a civil aircraft, a passenger aircraft, at least the larger sized ones like the Airbus A380 and many other, which is of course the recent one, and the Boeing 737s and 777s, all of them operate using what are known as the turbofan engines, and we will see why these aircraft would use a turbofan engine. It is basically because of fuel efficiency and many other reasons. Some of the smaller aircraft and helicopters use a different form of a turbojet engine, which is for an aircraft, these are known as turboprop engines. That is, there is a thrust component, a significant thrust component because of the propeller, and in the case of a helicopter, the jet engine just drives the main rotor blade, and the thrust and of course the lift is also generated both by the main rotor blade. So, we can see that the jet engines are used for a variety of applications. All of them happen to be some form or some variant of the turbojet engine. Now, when we have to analyze a turbojet engine, if you would have something we have discussed in one of our earlier courses, that is known as the cycle analysis, wherein we carry out some of the analysis, parametric analysis of the jet engine based on some of the design parameters that are known, like compressor pressure ratio, turbine inlet temperature, etc. And then we find out the performance of the cycle, like the thrust and the efficiencies, the fuel consumption, etc., based on some of these known parameters. So, we will take up the cycle analysis of real engines a little later in one of the later on lectures. Today, we will just look at the basic cycles of all these different forms of jet engines. So, one of the first cycles that we shall be discussing today is the turbojet engine. As I mentioned, turbojet is one of the most fundamental forms of a jet engine. It involves a few salient components which we will discuss shortly, and so the ideal turbojet engine cycle closely resembles that of a Brayton cycle, and we will see why it resembles when we take a look at the cycle of a turbojet engine. So, here is a schematic of a turbojet engine, a typical turbojet engine, and the different components of a turbojet engine are also shown here. Now, the first component of a turbojet engine is known as a diffuser. Diffuser is a component which decelerates the air to velocities which are suitable for that operation of a compressor. So, diffuser is followed by a compressor, and then the compressor delivers compressed air into the combustion chamber, where ignition takes place, fuel is added in the combustion chamber, and this is where heat addition in this Brayton cycle takes place. And downstream of the combustion chamber, we have the turbine, and turbine expands the air which is at high pressure and temperature at the exit of the combustion chamber, and in that process it delivers work output, and this work output is basically used to drive the compressor. So, turbine in a turbojet is mainly used for driving the compressor. At the exit of the turbine, there could be a component which is known as an afterburner. So, a turbojet engine may operate in a non-afterburning mode or an afterburning mode. We will discuss about afterburning a little later. You have already seen that in one of the earlier lectures. And then the exhaust combustion products then exhaust through a nozzle, which also generates thrust. So, these are the different components which constitute a turbojet engine, and there are some numbering schemes that you can see here, that each component is denoted by a certain number, which is just used in the cycle analysis that we will do for the actual turbojet engine in later lectures. Now, how does this look like in a TS diagram? We will see that a little later. Basically, the components, each of these components have a certain role to play in the whole Brayton cycle. And for example, the diffuser is part of the compression process. As we know, in a Brayton cycle, there are 4 distinct processes: a compression process, a heat addition process at constant pressure, then an expansion process, and again a heat rejection process. So, the compression process in a turbojet engine consists of 2 different components. One is the diffuser. So, part of the compression occurs in the diffuser, and then the rest of the compression occurs in the compressor. Well, most of the compression in fact occurs in the compressor, only a very small fraction of the compression occurs in the diffuser. Now, after the compressor, we have the combustion chamber. So, in a turbojet engine, you can see it is not really a heat addition process per se, it is combustion that is taking place, but of course, in the cycle analysis we replace this combustion by a heat addition process. So, heat addition in this turbojet engine occurs through the combustion chamber, and then after the combustion chamber is the expansion. Expansion again is split into 2. In a turbojet engine, we have expansion partly taking place in the turbine and rest of the expansion taking place in the nozzle. So, compression and expansion processes involve 2 different components, and in a Brayton cycle there is a last process, that is the heat rejection process. In a turbojet engine, there is no heat rejection per se, it is an exhaust process, that is combustion products are exhausted through the nozzle. And so, this process can be assumed to be the heat rejection process of a Brayton cycle. So, let us look at these different components and their functions in step by step. The first process, that is process between A to 1, is the diffusion process in the air intake, that is air from far upstream is brought to the air intake with some acceleration or deceleration, that is what is known as the pre-compression. And when we discuss about diffusers, we will understand why there are 2 different steps in diffusion itself. We will discuss that later on. And then the actual diffusion takes place, that is the internal diffusion or internal compression between stations 1 and 2. Compression occurs between stations 2 and 3, and we could have either an axial compressor or a centrifugal compressor. We will be discussing about these types of compressors in detail later on. We then have the combustion process between stations 3 and 4, and 4 to 5 is the expansion in the turbine. So, the turbine is primarily meant here in a turbojet engine to drive the compressor, and then there could be an afterburning taking place between stations 5 and 6, and 6 to 7 is acceleration and exhaust of the products through the nozzle. So, 6 to 7 is the nozzle process in the Brayton cycle or the turbojet cycle. Now, on a TS diagram, this is how an ideal turbojet cycle would look like. It looks very similar to that of an ideal Brayton cycle, just that the compression process is split into 2 processes here, and so is the expansion process. There are 2 processes you can see here. So, process A to 2 is compression in the air intake, and from 2 to 3 is compression taking place in the compressor. So, process between A and 3 is the compression process. In an ideal turbojet engine, this is an isentropic process. So, isentropic compression from station A to station 3. And then between stations 3 and 4, we have the heat addition or the combustion process, and so that is in a turbojet, ideal turbojet cycle, it is a constant pressure process. Between 4 and 7 is the expansion process, part of it is in the turbine, that is between 4 and 5, and between 5 and 7 is the nozzle, exhaust occurring through the nozzle. So, process between 4 to 7 is the expansion process in the nozzle. So, these are the different processes which constitute an ideal turbojet cycle, and we will discuss about real turbojet cycles in the in couple of lectures from now, where we will see what are the deviations that can occur in a real turbojet, and why is it that it is different from an ideal cycle, and what difference does it make to the performance of jet engine. So, we will discuss about some of these aspects in our later lectures. Now, as we have seen, turbojet can operate in two different modes, that is without afterburning and with afterburning. We have discussed about afterburning in some detail in one of the earlier lectures. Afterburning is basically a process wherein you can add additional heat or fuel in as in the case of turbojet to increase the temperature of the combustion products to much higher temperatures, and therefore, one can gain additional thrust by adding additional fuel. As we know that the air to fuel ratio in jet engines is substantially higher than the stoichiometric ratio, which means that there is much more air that is available after combustion, which can still take part in combustion. Therefore, after the turbine exit, there is substantial amount of air or oxygen which is still present, and therefore, it is possible for us to add additional fuel there without having to actually ignite, because the temperatures are substantially high. So, simply by injecting additional fuel, we can further raise the temperature at the nozzle entry, and therefore, the pressure as well, and this much pressure is available for expansion through the nozzle, and therefore, one can achieve additional thrust which could be used for so afterburning turbojet engines are basically used in aircraft, in military aircraft, especially when they need to accelerate to supersonic speed and cruise at supersonic speeds, and also carry out certain maneuvers. So, afterburning is not something that is used in civil aircraft, in turbofans and so on. So, it is usually used in a turbojet engine. So, with afterburning, there is a cycle which resembles a Brayton cycle with reheating. So, we have already discussed about Brayton cycle with reheating in the last lecture. Reheating is a process where we add additional heat after the first expansion process, which is exactly what happens in the case of an afterburning turbojet engine. That is, we add additional fuel and raise the temperature to a much higher level and expand all over again. So, turbojet engine with afterburning closely resembles a Brayton cycle with reheat. We will take a look at the turbojet with afterburning or reheat as well. And so, basically afterburning is something which is used when an aircraft needs substantial increment in thrust, for example, when it has to accelerate and cruise at supersonic speeds. And this is possible because the air to fuel ratio in gas turbine engines are much higher than the stoichiometric values, leaving sufficient amount of air which is available for combustion. And the other aspect is that after the turbine, there are no more rotating components and there is no more temperature restriction as such, and therefore, it is possible for us to have much higher temperatures than the turbine inlet temperature. At the turbine inlet, the temperatures are limited because the turbine blades have certain temperature restrictions, because it is also rotating at very high speeds, and so it cannot have we cannot have temperatures which exceed a certain limit, which is not a restriction in the case of an afterburner. So, it is possible to have higher temperatures than turbine inlet temperature. So, an ideal turbojet with afterburning would look something like what is shown here. So, the first process, the compression process is the same as that of non afterburning turbojet. It consists of two distinct processes or compressions. One is in the intake or the diffuser, and the second process between 2 and 3 is the compressor. 3 to 4 is the combustion process, which is the heat addition. 4 to 5 is the expansion in the turbine, and after the turbine exit is the reheating process or the afterburning process. Additional fuel is added, and so we have a process which resembles the heat addition here between 3 and 4. So, 6 to 6a is the afterburning process. 6a to 7a is expansion in the nozzle. So, here you can see that because the temperatures at the turbine inlet or turbine exit is now being raised to a much higher level, there is additional amount of energy or enthalpy drop which is available for expansion through the nozzle, and this is what results in additional thrust which one can achieve during afterburning process. So, if afterburning was not to be there, the nozzle would have only this much enthalpy drop for expansion, and now there is an additional enthalpy drop because of heat addition which has taken place during afterburning process. So, an ideal turbojet engine with afterburning is basically the Brayton cycle with reheat. So, Brayton cycle with reheat will have a cycle which is very similar to what we have just discussed about turbojet engine with afterburning. So, what we have discussed now is one of the most basic forms of the jet engines, and that is the turbojet engine, and we have also discussed about the ideal cycle of a turbojet engine, which very closely resembles a Brayton cycle, an ideal Brayton cycle. It has all the 4 processes as what a Brayton cycle would have, but the difference is of course in the last process, which is the heat rejection process, which is not really existing in a jet engine because it is an open cycle process, but the exhaust through the nozzle can be approximated to that of a heat rejection process. Now, one of the issues with a turbojet engine is the high exhaust velocity, and resultant high exhaust velocity is something which will affect one of the efficiency parameters which we have discussed, that is the propulsion efficiency. So, propulsion efficiency is directly related to the velocity ratios, the exhaust velocity to the flight speed ratio. And so, if we have to increase the propulsion efficiency, it is necessary that we have an effective exhaust velocity which is not very high. And so, in the case of a turbojet, a pure jet engine, the exhaust velocities can be quite high, and therefore, that affects the propulsion efficiency substantially. So, one of the ways of improving the propulsion efficiency is to try and reduce the effective jet exhaust velocity. And one way of doing that is to add another component to the basic turbojet engine, which will result in some reduction in the effective jet exhaust velocity. And one of the ways of doing that is to add a fan. So, ahead of a compressor, we now put a fan which will generate a greater mass flow, and this mass flow will be directed around the basic turbojet core, and this then later on mixes with the nozzle exhaust. And so, this form or variant of a turbojet engine is known as a turbofan engine. You have already seen this in some of the earlier lectures. And so, turbofan engine again can operate in different modes. We will see at least 2 different modes of operation of a turbofan engine, the unmixed form and the mixed turbofan modes. And so, turbofan engines have what is known as a bypass ratio, that is the mass flow passing through the bypass duct divided by the core mass flow is known as the bypass ratio. So, some of the modern jet engines which are used in turbofan engines which are used in transport aircraft typically have bypass ratios of the order of 5 or 6, which means that the bypass mass flow, the cold mass flow, relatively cold mass flow is 5 times the mass flow of the core engine. And so, there are 2 advantages to this. One is of course, that the effective jet exhaust velocities will be lower, which means propulsion efficiencies can be higher. The other advantage is that this additional mass itself can generate a thrust, and therefore, you get an additional thrust and also a slightly better propulsion efficiency, which means that the overall efficiency can also be better than that of a pure turbojet engine. So, the need for a turbofan engine is basically to reduce the effective exhaust velocity, and therefore, we add a fan which has a larger diameter than the compressor, and therefore, that generates a higher mass flow than the core mass flow. So, this ratio basically the cold mass flow to the hot mass flow is known as the bypass ratio. And so, for the same speed range, turbofan engines will have a higher propulsion efficiency than turbojet engines, basically because the exhaust velocities are lower, and therefore, it obviously means that we get a better propulsion efficiency than a pure turbojet engine. Of course, there is another advantage of turbofan engines, in the sense that turbofan engines generate lesser noise. Jet noise of a turbofan engine is lower than a turbojet engine. This is again related to the jet exhaust velocities, because a very high speed jet, when it expands into cold ambient, leads to a lot of noise, whereas in the case of a turbofan engine, the speed of the jet, effective speed of the jet is lower, and therefore, the jet noise of such engines are lower than that of the pure jet engines. That is another advantage of turbofan engines, because in the current scenario, the noise restrictions are also getting stringent every year, and so aircraft engine manufacturers need to stick to certain noise norms, in the sense that the noise levels of jet engines need to be lower than certain levels which have been stipulated, and so every few years these norms are revised, and it gets stricter every time it is revised. So, it is necessary for engine manufacturers to adhere to all these norms, and so turbofan engines have that additional advantage as well, because these aircraft have to take off and land in airports which may be close to civilian regions, and so it is necessary that the noise levels are under control. So, let us now look at a schematic of a turbofan engine, one of the forms of a turbofan engine, and we will immediately see what makes it different from a turbojet engine. So, this is one schematic that I have of a turbofan engine. This is basically an unmixed turbofan engine. I will explain what is unmixed shortly. And you can see that the fundamental difference between this engine, which is shown an unmixed turbofan, and a pure turbojet, is the first component that you can see here, well, rather the second component, that is the fan. In a turbojet, this fan was non-existent, and therefore, after the diffuser we had a compressor, the combustion chamber, the turbine, and the nozzle. In a turbofan, we have this additional component, and so this fan diameter, as you can see, is much larger than that of the compressor, and so this will be able to generate a greater mass flow, which will pass through this bypass duct. So, there is a bypass duct which surrounds the core engine, and then this bypass duct will exhaust through a secondary nozzle in the case of an unmixed turbofan. And so, after the diffuser we have a fan, part of the fan mass flow goes through the compressor, but a larger mass goes through the bypass duct, which gets exhausted through the secondary nozzle. Then we have the usual turbofan here for the turbojet for the core engine, that is a compressor, then a combustion chamber, then expansion in the turbine, followed by the primary nozzle. So, these are the various components of a turbofan, an unmixed turbofan, and at least the core engine here closely resembles a pure turbojet engine. Now, what about the second variant of this engine? We have a mixed turbofan here. In a mixed turbofan, you can see that there is only a single exhaust from such an engine, that is, the bypass mass flow mixes with the turbine exhaust, before it exhausts through a common nozzle. Whereas, in the unmixed turbofan, we had two separate nozzles. One was a bypass nozzle or the secondary nozzle, and the primary nozzle, which was from the core engine, the hot nozzle. In a mixed turbofan, there is a single nozzle, and the bypass mass flow mixes with the turbine exit mass flow before it gets exhausted through a common nozzle. So, these are two variants or two different types of turbofan engines. So, turbofan engines can exist in these two different modes or forms. For transport aircraft, it is the first form, that is the unmixed turbofan, which is more commonly used, and in some of the recent military aircraft, we have the mixed turbofan with a very low bypass, which is something we have seen in some of the earlier lectures. That very low bypass turbofan, of course, it very difficult to say whether it is a turbofan engine, but it has a small bypass with a very small mass flow, and therefore, it gets classified as a turbofan engine, which is mixed and a single nozzle exhausting. And what are the different processes which are involved in a turbofan engine? Well, it is very similar to that of a turbojet. Most of the processes are common, except for the first few processes which involve the fan and the bypass nozzle and so on. So, the different processes, let us say in an unmixed turbofan, will be the following. We have the diffusion taking place between stations A and 2 prime, and then we have compression in the fan between 2 prime to 3 prime, compression in the nozzle, compression in the compressor, which could be axial or centrifugal, is between stations 2 and 3. So, 2 to 3 is compression in the compressor. Then there is a combustion chamber between 3 and 4, and between 4 and 5 is a turbine, and 5 to 6, because there is if it is unmixed, there is very little chance that there is any afterburning here, but in a mixed turbofan there could be an afterburner as well. And between 6 and 7 is the primary nozzle, and the bypass duct also has a nozzle, which is the secondary nozzle, and that also generates a substantial amount of thrust, basically because of the mass flow that the fan generates. So, the different processes in a turbofan engine as compared to that of a turbojet engine is, the differences are basically because of the presence of the fan and the bypass duct. And in the case of, let us say, an unmixed turbofan or even a mixed turbofan, sometimes it is also possible that we may have to split the turbine into different stages to enable us to drive the fan and the compressor at different speeds, because the fan has a much larger diameter than that of a compressor. Therefore, in an unmixed turbofan, it is necessary for us to drive the fan and compressors at different speeds. And so, one of the ways of doing that is to use a multi-spool engine. We have already seen what is multi-spool engine, what are different forms of those. It could be twin spool or a 3-spool turbofan, which means that the fan is driven by one of the stages of the turbine, usually the last stages of a turbine, that is the low pressure turbine, and the compressor is driven by the high pressure turbine. And you could, if it is a 3-spool turbofan, then the compressor itself is split into two, the low pressure compressor, the LPC, and the high pressure compressor, the HPC, which are driven by again two different stages of the turbine, and one of the stages of the turbine driving the fan. So, these are basically meant to drive the different components at different speeds, because obviously it is not possible for us to drive all of them at the same speed, because the diameters are quite different. And so, if we were to drive, for example, the fan at the same speed as that of the compressor, then the tip speed of the fan obviously would be much higher than that of the compressor, and so there are other issues like shock losses and so on, which will come into picture. We may be discussing this when we discuss about compressors in detail later on. So, it is for this that we have to split and drive these components at different speeds. And so, in unmixed turbofan, this is one of the issues that these may have to be driven at different speeds. Now, if you look at the thermodynamic cycle of a turbofan as compared to a turbojet, they look more or less very similar, except that we would have one more cycle for present for the bypass stream, because for an unmixed turbofan, the core stream and the bypass streams are entirely different or separate, and therefore, the bypass process itself is entirely different. So, so we could have another cycle which is meant for the bypass stream, and there is no heat addition occurring there, and so it's basically not part of the core bypass, the core Brayton cycle mode. Whereas the core engine is very similar to that of a turbojet, and so the cycle is very much the same as what we have discussed. And what we will also be discussing maybe in one of the later lectures is about the how is it that we can analyze a real turbofan engine, that is a turbofan engine which has all those losses and irreversibilities accounted for, and how can we carry out a cycle analysis of such engines and get estimates about their performance in terms of thrust and efficiencies and fuel consumptions and so on. We will discuss that in one of our later lectures. And so, the next set of engines that we will be talking about are the turboprop and the turboshaft engines. Turboprop engines, as you know, is a class of engines which generates substantial shaft power, and there could be of course turboprops which also generate nozzle thrust, besides the majority through the shaft power itself. Turboshaft engines, on the other hand, it generate only shaft power, and these are used in helicopters, and the shaft power which these engines generate is used to drive the main rotor blade. And in a turboprop engine, what we aim to do is to incorporate the advantages of a propeller based engine into a jet engine. As we know, the propeller based engines have very high propulsion efficiencies, and the propulsion efficiencies of pure jet engines are much lower as compared to propeller based engines. So, if we were to combine both these engines together and see if we can get a better propulsion efficiency by combining these two. So, turboprop engine is one way of trying to use the advantages of the propeller type of engines and the jet engines, and therefore, turboprop engines have higher propulsion efficiencies as compared to pure jet engines. And turboshaft engines on the other hand, of course, do not generate any nozzle thrust, they primarily generate the shaft power. But both turboprops as well as turboshaft engines are meant to operate at lower speeds as compared to pure jet engines, and they have applications at relatively lower speeds and lower altitudes as compared to pure jet engines. Now, this is a schematic of a typical turboprop engine, and let us take a look at what are the different features or components of a turboprop engine. So, one of the most prominent components of a turboprop engine is the propeller. So, this, as you can see here, is the propeller, and propeller is driven by a turbine which is usually referred to as power turbine, or sometimes also referred to as a free turbine. And the shaft power from the turbine is transmitted to the propeller, usually through a gearbox, because it may be necessary to reduce the speed of the turbine exit shaft, because propellers may not be running at very high speeds. And propellers may also have certain pitch control mechanisms if they have to be altered during flight, during the different changes in altitudes and flight conditions. And then the other components which constitute this engine are similar to that of a jet engine. There is a compressor, and then a combustion chamber, and then at the exit of the combustion chamber there is a nozzle, well, there is a turbine, and this turbine is usually referred to as the compressor turbine because it drives the compressor. And from the exhaust of this turbine, there is a power turbine. This power turbine is meant to drive the propeller, and then exhaust of this power turbine goes through a nozzle which may generate some amount of thrust. And so, the difference between a turboprop and a turbo shaft is basically that in a turbo shaft engine, the thrust developed by the nozzle is negligible, and so a propeller is replaced by the main rotor blade, and so the power turbine drives the main rotor blade, and there is negligible nozzle thrust generated by turbo shaft engines, but the rest of the cycle and the components remain the same. So, here again you can see that many of the components are common to that of a turbojet engine, like compressor, combustion chamber, turbine. So, these components are present even in a turbojet. It is also present in a turbo shaft, a turbo fan engine, and obviously it is also there in these engines, that is turbo prop and the turbo shaft engine. So, many of these components are common, and the difference between these variants of the basic turbojet is in the presence of certain additional components like the fan and the bypass duct and the secondary nozzle in the case of the turbo fan engines, and the presence of the propeller or the main rotor blade in the case of turboprop or turbo shaft engines. So, these components basically make these variants of pure turbojet engine. Now, both turboprops and turbo shafts have, as we have seen, a separate turbine which is known as a free turbine or a power turbine, which drives the propeller in the case of turboprop, or the main rotor blade in the case of a turbo shaft engine. And so, this particular turbine is known as a free turbine or a power turbine because it is not driving any of the compressor stages. It is driving just the propeller or the main rotor blade. And because of limitations in the maximum speed that these propellers or the rotor blades can rotate, it would be normally required to reduce the turbine shaft speeds to lower values, and that is why we normally use gearboxes in turboprops and in turbo shaft engines. And in the case of turboprops, sometimes there could also be a certain amount of thrust which is developed by the nozzle, and so there could be a nozzle thrust developed in turboprop, which is not really present in turbo shaft engines, because turbo shaft engines primarily develop the thrust because of the presence of the main rotor blade. Now, in the case of turboprop engines, basically the thrust may consist of two components, one because of the propeller thrust and the other is the nozzle thrust, and therefore, the total thrust is the sum of these two, the nozzle and the propeller thrust. And in the case of turbo fan engines, again the unmixed turbo fans, a very similar thing happens. There is a thrust component because of the bypass duct, and there is also a thrust component because of the core mass flow. Total thrust will be the sum of the bypass and the core thrusts. Now, in the case of a turboprop or a turbo shaft engine, one of the differences between this and the basic turbojet engine is the free turbine. That is, free turbine is one of the components which distinguishes turboprop and turbo shaft engine from a turbojet engine. And so, if you look at the free turbine here, this is the free turbine that is shown, which is present between stations 5 and 6. And so, there is an enthalpy drop which is occurring in the free turbine, and that is between stations 5 and 6. So, the total enthalpy between stations 5 and 6 drops, and you can see there is a pressure drop, total pressure drop as well between 5 and 6, and the rest of the expansion occurring between station 6 and 7, which is the nozzle. In the case of turbo shaft, of course, 6 and 7 are the same points, and therefore, the expansion is entirely between 5 and 6, and which is what it would be in the case of a turbo shaft engine. And so that is one of the differences between the turboprop and the turbo shaft, in the sense that in turboprops it is also possible to have certain amount of thrust, certain expansion which continues after the free turbine in the nozzle. So, certain amount of thrust is still developed by the nozzle, whereas in the case of turbo shaft the entire enthalpy drop occurring during the expansion process occurs just across the turbine stages, which is the compressor turbine as well as the free turbine stages. So, that is once the expansion is no longer split into the compressor and the nozzle. Here in the case of turbo shaft, it is entirely through the turbine exhaust, and so that is what it makes a difference between pure turbojet and these propeller or turbo shaft engines, the presence of the free turbine. So far we have been discussing about jet engines which involve rotating components, like in the case of, in fact, all these engines we have been discussing have compressors and turbines which are rotating in nature. So, all these components, all these forms of engines have turbo machines, and so these are one class of engines, jet engines, which use turbo machines for their operation. And there is another simple form of a jet engine which we will discuss now, which are known as ramjets, and ramjets do not have any of these rotating components. So, without the presence of any of these rotating components, it is still possible to develop thrust with certain conditions we will discuss. And so, you may wonder, how is it that it is possible to have a jet engine which can develop thrust without having any of these rotating components? Well, it sounds very simple, and schematically also it looks very simple, but its operation is not as simple as what we would expect it to be. And so, ramjets are the simplest form of jet engines, in the sense that they do not have any rotating components, they do not have compressors, and therefore, they do not have any turbines, but they do have air intakes, combustion chambers and nozzles. So, using these three components, simple components, it is possible to generate thrust, and we will see why is it that it is, in spite of being so simple, it is not commonly used. We will discuss that little later. So, ramjets are the simplest form of jet engines, and they basically have just three processes occurring: a compression process occurring in the intake or the diffuser, a combustion process occurring in the combustion chamber, and an expansion process through the nozzle. So, using three different thermodynamic processes, it is still possible to develop thrust. So, the ramjets operate based on this. So, ramjets are supposed to be most efficient only when they operate at supersonic speeds, and the basic principle behind the ramjet is that when air is decelerated from a very high Mach number to very low subsonic Mach numbers, it results in substantial increase in pressure and temperature. We have discussed this earlier in the earlier course, and if you have gone through gas dynamics course, you would know by now that if air is decelerated from very high Mach number to very low Mach number, this requires, of course, the use of shocks and so on. There is a substantial increase in the pressure and temperature, and if that is the case, you do not really need a compressor, because the air is getting decelerated anyway without using compressors, and there is an increase in pressure and temperature. So, with this in mind, you do not really need a compressor, because pressure and temperature has already been raised, and since you do not need any compressor, you do not really need a turbine as well, because a turbine is basically meant to drive a compressor, and if you do not need a compressor, you do not need a turbine as well. Now, so let us look at a schematic of a ramjet. I mentioned that it is very simple, and it is indeed simple to look at the schematic, that it consists of a diffuser, a combustion chamber and a nozzle. Of course, the diffuser is slightly complicated. It is a supersonic diffuser. It has one component which is known as a supersonic compression, and then followed by a subsonic compression. At the inlet of the combustion chamber, there are injectors, fuel injectors, which initiate combustion, and there are flame holders to ensure that the combustion is stable. And then at the exit of the combustion chamber, we have a nozzle. So, this type of diffuser geometry, which consists of supersonic compression, subsonic compression, we will discuss this later on when we take up diffuser analysis in detail. So, this is a schematic of a ramjet, and since it consists of only 3 processes and no turbo machines, that makes it design of ramjet very simple, at least theoretically. And so, even on a cycle, if you look at a ramjet cycle, it is very similar to that of a pure turbojet cycle or a Brayton cycle, consisting of a compression process, a heat addition process. For an ideal ramjet, it is at constant pressure, and an isentropic expansion. So, with these 3 different components, it is possible to achieve thrust using a ramjet. But the precondition for operation of a ramjet is that it has to operate at a certain speed before ramjets can themselves be operational. Because ramjets do not have compressors and turbines, a stationary ramjet cannot generate any thrust, it cannot operate at all. So, for a ramjet to begin its operation, it must be taken to a certain speed, because ramjets require that the incoming air can get compressed on its own by virtue of the diffuser geometry. So, if that has to happen, ramjets themselves have to be taken to a certain speed before which they can start operation, and ramjets generate maximum thrust at very high supersonic speeds of around Mach 3. So, at around Mach number of 3 is when ramjets operate most efficiently and generates the maximum thrust. And so, below Mach 3 the performance is suboptimal, and at very low Mach numbers ramjets can hardly operate on its own. So, ramjets need to be taken to a substantially high Mach number before which they can begin to operate. So, a TS diagram of a ramjet cycle, an ideal ramjet cycle would look like this. There is an isentropic compression taking place in the intake, followed by combustion at constant pressure, and then there is an isentropic expansion through the nozzle between stations 4 and 7. So, this is how an ideal ramjet cycle would be, very simple cycle, and resembles a Brayton cycle very closely. Now, in a ramjet engine there are no compressors and turbines, and therefore, its analysis is quite simple, because you do not have too many complex geometries present in ramjet. And so, ramjets cannot generate any static thrust, basically because ramjets depend upon ram compression without the use of compressors, and therefore, they cannot generate any static thrust. Ramjets have to be taken to sufficiently high speeds. There is a certain speed beyond which only then ramjets can begin to generate thrust of its own. So, ramjets have to be taken to a certain speed before which they can start generating thrust. So, that is the basic limitation of a ramjet, that it cannot generate thrust, static thrust on its own. So, what we have discussed today is the different types of jet engines. We started our discussion with the basic type of a jet engine, the turbojet engine, and different forms of the turbojet engine. Then we have also discussed about turbojet engine with afterburning, and then the variants of a turbojet engine. We started with turbofan and different forms of the turbofan engine, the mixed and unmixed turbofan engines. We also discussed about turboprop engines and the turboshaft engines, and then of course, we also discussed about ramjet engines, which are the simplest form of a jet engine. So, these are some of the topics we have discussed in today's lecture, and we will continue with our discussion on jet engines in the next lecture as well. In the next lecture, we will be discussing about the different components which constitute a jet engine, and how can we account for the performance of these components. We will discuss about the air intake or the diffuser, the compressor or the fan, combustion chamber, turbine, and the nozzle. So, these are the different salient components of a jet engine. We will discuss about the performance of performance parameters which need to be considered for cycle analysis of an actual jet engine, and so we will discuss about these in our next lecture, and subsequently we will take up the cycle analysis of actual jet engines. We will be carrying out cycle analysis of all these jet engines that we have discussed, and we will also account for the component performance variation occurring across all these different components. So, we will take up discussion of these topics during the next lecture.